Hello everyone, I am Pınar Satılmış from Birmingham City University. Today I will present you my talk entitled Skylighting for Graphics Applications. In this talk, we will mainly cover skylighting methods for graphics applications. To start with, we will look into image generation techniques briefly. Then, the methods to generate clear and cloudy sky illumination will be investigated. We will also investigate models based on machine learning techniques. In computer graphics, rendering methods are used to generate images from 3D scenes. To generate an image, we need 3D models, light sources, and a camera. In this talk, we will cover the light sources for rendering. In graphics, illumination from realistic skies is an important component of image synthesis. How we perceive the scenes is affected by the light source. On a sunny day, there are sharper shadows and more distinctive colors, where on a cloudy day, we perceive a darker scene, as in these examples. Sky is the main light source for outdoor scene illumination, but it is also responsible for illuminating the indoor scenes. Indoor scenes can receive light from windows. As we have seen in the previous example, we can also see in these indoor scenes that the scene illuminated with clear skylight, which is on the left, looks brighter and has sharper shadows, but the one on the right, which is illuminated with cloudy sky, looks darker and doesn't have distinctive shadows. Rendering is a commonly used technique in many fields. For example, in architecture, predicting the appearance of a house before investing money on the construction can help the architects to save money and time. It also helps them to get accurate predictions of the house. Especially, it is possible to predict how much light it will receive when it is completed. Computer-generated imagery is also used for generating catalogs. Creating real rooms and capturing their photos is a time-consuming and hard task. Instead of it, 3D models can be used to generate images. Here we can see some examples from IKEA. One of these photos is computer-generated. Which one would you say? The one above is a computer-generated one, and the one below is a real photograph. As you can see, it is quite hard to understand the difference between them. Rendering methods are also used in entertainment. As in this example, we cannot find an alive dragon now, but we can render one which looks real enough to convince the audience. Creating images from 3D scenes is implemented by solving the light transport equation. The rendering equation is a formulation of light transport introduced to computer graphics by Kajié in 1986. This equation formulates the incoming light in a given direction by calculating its interaction with the scene objects. as illustrated here. The perceived light can interact with many objects in the scene until it reaches the eye or the camera. Let's investigate the equation a bit closer. We can see it has mainly two components. The first equation tells us about the emitted radiance in the viewed direction by the light source or the objects which are emissive, such as flame, sky, or artificial light sources. The second function tells us about the reflected light into the given direction. The third one is the BRDF function. BRDF tells us how much of the incoming light will be reflected by using the ratio between the incoming and reflected light. For example, if the light source is white, we perceive it as red because of the object's reflectance properties described by the BRDF. And the last one is the cosinus function. Cosinus weighs the radiance for the brightness. When the light approaches with a vertical angle to the surface will look brighter. There are different ways to solve the light transport equation. Ray tracing is one of them, which can generate photorealistic outputs. This slide illustrates the ray tracing method. Ray tracing iteratively estimates the light coming from a direction after traveling throughout the scene, starting from the light source. Light is represented as rays, and different rays are considered in ray tracing, such as reflected ray, refracted ray, shadow, and primary rays. As can be seen from figure 2, light sources are a requirement to solve the rendering equation. Rendering of the scenes with participating media is achieved by solving the radiative transfer equation. Smoke, clouds, air are a few examples of a participating media. This equation formulates the scattering of light from the particles inside the media. To solve this equation, we need to consider the transport of the light as in-scattering, out-scattering, absorption, and emission. As can be seen, this equation also depends on the existence of a light source. Today, we are going to look into natural light sources, skies. Sky illumination is investigated as clear and cloudy skies, since they require different techniques to be implemented in computer graphics applications. We will start with clear sky lighting. There are mainly two methods to implement clear sky lighting: using of analytic functions and image-based lighting. We will first look into analytical functions, then investigate the image-based methods. Analytic functions are the complex way of modeling the sky lighting. In 1993, Perez was the first to develop a model of the clear sky for graphics applications. Later, in 1999, Pritham updated this model by adding atmospheric conditions to this model. The latest model is given by Josek Welke. Prism and Hossack-Wilk sky models are the most commonly used analytic models. Both of the sky models depend on the idea of fitting coefficients for the model. The most general model is proposed by Hossack and Wilke, which can generate sky illumination for a wide range of turbidity and ground albedo values. We can see the model in this slide. As can be seen from the equation, despite being able to generate a wide range of sky scenarios, this model is computationally expensive, especially for real-time applications. And this is an example of sky lighting generated with Hossack-Wilke model. The other approach is to use environment maps. Environment maps are special image types which can store light information. This slide shows an environment map in latitude-longitude format. These images are captured with special devices and only stores the light information for the capturing moment. Therefore, it can only store sky lighting for one sun direction. For daylight animation, more environment map captures are necessary. But when the sky is captured sparsely, the resulting skylight will not be smooth, as illustrated here. Let's have a look at the video. We can see the jumps in between frames. In many cases, for outdoor scene illumination, we need a daylight animation. To do so, the researcher should do more frequent capturing. We can see that this is a hard task, considering especially when capturing an outdoor scene where one cannot leave the camera alone. Also, storing a large number of images would be another problem. An alternative to these traditional techniques is to use machine learning techniques, specifically artificial neural networks. ANNs are fast to compute and an easy and efficient way to learn. In this method, we used a single-layered ANN with 8 neurons in the input layer, 12 neurons in the hidden layer, and 3 neurons for each RGB values in the output layer. Having a single hidden layer makes this method fast to compute. Let's have a look at the input feature vector a bit closer. The inputs are 8 features describing the sky scenario and view direction. Specifically, the turbidity is one of the features, the turbidity value. This value describes the haziness of the sky. Sun altitude is the given other feature value. In this research, the azimuth angle of the sun is kept fixed, only the altitude value is used. View direction is the next feature. It is defined in Cartesian coordinate system. And the last feature is the distance between view and sun direction. Distance value helps to encode the view and sun direction. Hence, it improves the training. ANN model can learn different sun positions and turbidity values and return the illumination for a specific direction with a sky scenario in the range of training set. For this research, we used analytical functions and environment maps for training. For analytical models, we use two state-of-the-art models proposed by Pritam and Hossack-Welky. In the case of environment maps, three different datasets are used separately. One is captured in Portugal, the other one in Egypt, and we also use the dataset provided by Kider et al. These environment maps, the datasets, all include sparsely captured images throughout a day. Let's see some training results. This example shows the difference between two environment maps by pixel-wise comparison. Each row is showing a different sky scenario examples. The ones on the left is showing the reference image, where the ones staying in the middle are the outputs of the neural network model. And on the right, we can see the difference image between the two images. The difference image is looking close. The difference between the two images are close to 0 pixel-wise, which makes the difference image look close to black. Hence, we can say that the neural network model learns the reference image with low error. ANN is capable of generating intermediate sound positions. In this example, we can see the interpolation of sparse data, which is missing in the second row. The missing data is completed by the ANN model shown in the first row. Another example for interpolation. Here in the second row, we can see the missing data, and the prediction is by the ANN model is shown in the first row. In this example, we can see an example of training of environment maps. The video on the left shows the sparse capturing of the daylight, and the one on the right shows the ANN approximation, which can generate a smooth daylight animation from sparsely captured data. In this slide, we can see another example. This example highlights the effect of the neural network skylight on different surfaces. Here, we can see three different types of materials: diffuse, glossy, and mirror surfaces from left to right, illuminated with neural network sky model. ANN sky model is fast to compute and can run in parallel. In this slide, we can see it working in real time. GPU implementation shows the low memory cost of the method. Let's have a look at the quantitative results. The first table shows RMSE results. You can see that this table is presenting two analytic functions, Pritam and Hossack models, and two environment maps, the ones captured in Egypt and provided by Kider. We can see that the method can learn the input skies with high accuracy. The method can learn the illumination with an accuracy more than 96%. In photorealistic rendering, we aim to achieve realism close to the real world. Therefore, we also would like to achieve the accurate irradiance values or low irradiance error. And the presented irradiance error, it can be concluded that the method can be used to illuminate the scenes with low error instead of the sky models in the training set. In the case of the analytic sky models, the presented method reduces the computational time of the current state of the art sky models. Here we can see Pritham and Hossack-Wilke sky models. We can say that neural network model improves the timing almost up to 3 times compared to these models. Now we investigated the clear sky models, but real skies also include clouds, which need to be considered for graphics applications. The cloudy lighting in graphics can be achieved mainly in 2 ways. The first way is to capture the sky with special cameras in an HDR format. This is a time-consuming task, and it is only feasible to capture cloud images with a limited number of cloud types and configurations. So as illustrated here, the researcher can capture the cloudy lighting for the moment of that capturing, and the cloud structure or the positions of the clouds will depend on their position. It's hard to capture the cloud in the position that we would like it to be. The other method is to simulate the light transport through the atmosphere. This requires modeling a realistic 3D cloud volume and simulating the interaction of the light with the atmosphere. So we can see an illustration here. As you can see, the light simulation includes the traveling of the light throughout the atmosphere and interacting with the particles inside the atmosphere. When the large size of the atmosphere is considered, computing a noise-free image would require simulating a significant number of light paths, which makes this a computationally heavy task. So as we have seen, the traditional ways has limitations. Capturing requires costly devices and finding the right moment to capture the sky for the specific sky scenario, and simulating the atmosphere for clear sky lighting is a computationally heavy task. Here we are providing an alternative to these methods to leverage deep learning methods. In this method, we don't need to do any sky capturing. It doesn't require any rendering, therefore we don't need any complex 3D cloud models. It also doesn't suffer from heavy computations. Furthermore, it is possible to simulate any atmospheric scenario. The method generates cloudy sky lighting only from a given sky scenario and a cloud mask. Let's have a look at an overview of the method. In this method, the user provides a cloud map along with a sky map. Maps are represented in fisheye format. A cloud map is a binary mask which illustrates the areas covered by the envisioned cloud. It can be generated even with the Paint application. The user only needs to sketch the cloud boundary for the cloud shape they would like to create. A sky map is a clear sky lighting that the user would like to form the clouds with. This can be generated in different ways. In this research, we use Hosack-Wilk sky model. For the given two maps, CloudNet estimates cloudy sky illumination. Let's look at the network structure a bit closer now. CloudNet has U-Net structure, which is composed of encoder and decoder layers. U-Net is chosen for its, in this research for its success in decoding the information and also being able to provide high frequency details. The inputs to the network are a distance map and a clear sky lighting. Distance map is estimated from the cloud mask, which we described in the previous slide. This is demonstrating the shape of the clouds, and the initial research showed that the distance map estimated from the cloud mask improves the learning accuracy. Therefore, we feed the network with distance map rather than the cloud mask. Clear sky lighting demonstrates a sky scenario for the clouds to be generated. CloudNet encodes the cloud map, the distance map and the sky map into lower resolutions through the encoder layers. And the cloudy lighting is generated by decoding the encoded images progressively through the decoder layers by combining them with the encoder features. We generated our dataset from 360-degree cloudy sky images. In this slide, we can see examples of clear sky and cloud mask, which are obtained from these images. To feed into the network, we generate a distance field map from the estimated cloud mask, which is shown on the right. To estimate the clear skies from cloudy sky images, we used histogram matching technique. Here we can see an example of histogram matching between the ground truth, shown on the left, and the estimated Hosack-Wilk sky map on the middle. The image on the right shows the histogram matching result. At this table, we can see the results of the conducted ablation study over 4 types of loss functions. These functions are chosen for their success in generating high-frequency details in the clouds. R/B ratio is a commonly used loss function to classify cloud and sky pixels. As we can see, using 4 loss functions together minimizes the learning error. Let's have a look at the results that we got with this method. In this figure, we can see examples of generating cloudy sky lighting with the proposed method. Here, given the cloud mask and sky map, we can see that our method can produce images closer to the ground truth data. We can see the CloudNet results and the reference images on the last 2 columns. Please pay attention to the similarity between these 2 images. We can see another example in this slide. Some more results are presented in this slide. We can see a selection of synthesized CloudNet images and their references. CloudNet outputs are shown on the left and their references are shown on the right. We can see more examples in this slide. We can see some more results generated with the CloudNet. In this slide, we show examples of generating clouds using the same hand-drawn segmentation masks presented on the left with different skies. Please pay attention that the sky images within the same row presenting different sky scenarios. And we can see that changing the sky light also changes the lighting of the clouds. We can see further examples in this slide with a different cloud mask. Please pay attention to the teapot-shaped mask, which created a plausible cloud lighting. In this slide, we can see some triplet examples. CloudNet can produce cloud lighting which matches the input sky scenario. These three triplet examples emphasize how CloudNet is adapting the output sky to be closer to the natural sky rather than just compositing clouds onto the sky map. In this slide, we will see some juxtaposition demonstrations. The illumination generated by CloudNet is consistent across the sky. To demonstrate it, this example shows composites of the ground truth and the synthesized outputs split on the horizontal axis. We can see the smooth transition from left to right. And some rendering results. We said that we are going to use this cloudy sky lighting for computer graphics applications. This example shows renderings using synthetic cloud maps with a dog-shaped cloud under different stand positions. Illumination changes in both the environment map and the scene are clearly visible. Some more results. This example shows results for rendered scenes lit by CloudNet environment maps and the same renderings without any cloud coverage. This shows that plausible illumination is generated by the network and can be used as a light source for image synthesis. In this slide and in the next slide, we are going to see the summary of our methods in videos, presented as videos. Thanks a lot for your attention.